We're going to start with diffusion getting today. This is the last topic of our waves chapter. Keep watching. If you have any question, you ask me about it. Grating essentially means a very series of hole. For example, it's sort of like a filtration device or something like that. Uh, Diffusion getting is a certain equipment that we use to work with light diffraction, and it is essential to work with lights which are of high frequency. Let me show you why is that. Let me just tell you why this is necessary in the first place. The double slit experiment for our discussion that had a situation like this. If we have two sources over here and here, and if the light is making a pattern over here where the source is giving us light of wavelength lambda, the slit separation is A, the distance from the sources to the screen is D, in which case we can get, let's say, bright, dark, bright, dark, dark, bright, like that. So we can get the fringe separation that is defined as X. This is a very basic uh, figure for the double slit experiment. The equation that relates to all of these variables is given by lambda equals to X by D, or we can write that if I subject X from here, I have a reason why am I subjecting this. I'll discuss this in a bit. I'm gonna get lambda D divided by A. Now, the problem is that if we want to work with lights with a high enough frequency, I mean, the idea is that if we want to work with this experiment, primarily we need a reliable and achievable way so that we can measure the X properly. Being able to measure the fringe separation is really important with appropriate accuracy and reliable uncertainty. So you cannot have a measurement that where your uncertainty is more, or let's say close to 50% of your actual measured value, because that's not very reliable. So have a look at this variable. If we want to do this experiment, double slit experiment, for a really high frequency wave, for example, purple, blue, or even we go for the uh, uh, invisible part of the electromagnetic spectrum, if we go for X-rays or gamma rays, whenever the frequency goes up, lambda becomes inversely proportionally small. So for high frequency lights, this lambda is going to be pretty small, which is something that we cannot vary if we want to work with high frequency light. We just have to deal with light with smaller wavelengths. So this is a problem that we're going to have. Problem number one. Problem number two is that, so this will essentially make the X value significantly smaller. So having the X value significantly smaller essentially means this entire pattern is going to get squashed. Squashed means the central maximum would pretty much remain at the central maximum position. The central maximum will pretty much remain at the central maximum position, but the entire thing is gonna become squashed from both sides. So the whole pattern is gonna become squashed, so that your X become reduced. Now, up to a certain value, this small measurement can be done, but whenever you go for really high frequencies, this can prove a significant trouble. You might wonder that, well, this is a trouble that we have, fine. Then how about to compensate for the decrease of X, how about we increase the D? Because if we increase the D, logic tells us that X should be increasing. Well, that sounds like a promising solution, but only the problem is that it is not, because increasing the D essentially means taking this screen further away from these sources. Whenever we'll take this screen further away from the sources, the intensity of the bright fringes will become pretty dim, because as we get further from the source, intensity of a light wave decreases in the inverse square proportion of the distance. So there is a square even, which means the farther we're gonna get, the intensity of the bright fringes is gonna get reduced by a square factor. doubling the distance will give you 1/4 of intensity. So all the bright spots are going to become pretty dim. You might have them pretty far apart, but they will lose their brightness significantly. So, and it's not very logical, or it's not very helpful to work with a dim pattern where detecting the bright fringes and dark fringes, especially on the borderlines over here, close to the central maximum, it's usually quite visible. But as we slowly get further away, the brightness of the bright fringes become less and less because of attenuation. Attenuation is the word. Attenuation. Attenuation. I'm not telling you the. I'm not going to tell you the exact definition of attenuation, but the way attenuation essentially means the reduction of a signal power or intensity as it goes over distance. That's what we mean by signal attenuation. The reduction of signal power or any wave power / intensity as it goes over distance. That happening of reduction of power is what we call attenuation. So this equation is basically a mathematical relationship for the attenuation thing. So as we go farther away from the central maxima, above or below, we're going to have less brightness onto the on the bright skin spots, which is a problem. This whole pattern is going to become pretty less visible. The next, so, and also in a laboratory, how much within how much space are we going to be able to, are we going to do this experiment? It actually has a limit. You cannot have a laboratory that is, let's say, 10 meter, 20 meter long, just for you to perform this experiment, and that's not actually practical. So for what can I say, for logical sense, or for basic constraints of physical space and also the brightness reduction, we have to keep D in a convenient value. So somewhere around 1 meter to 2 meter is typically the max range for we use for D. And then comes the point of A. So you can see that increasing the D by a very significant amount, for example, 10 times, 20 times, is not a possible option. So we cannot essentially work with this. So the last variable that we have left is A. You can see that the A is over here on the right side on the denominator side. So if we want to have the X value increased, we have to reduce the value of A, which means we have to bring these two sources pretty close to each other. Now, one of the problems that happens that whenever we are going to bring these two sources really close to each other, this entire pattern is going to get pretty wide, which is a good thing. But one thing is that whenever we bring multiple sources pretty close to each other, this whole the diffraction of the two light waves start to behave like a single slit. For example, single slit means that diffraction pattern for a single slit is not actually covered in a syllabus, but they start to give some problem. So essentially, this is what we're going to do for light waves. So in the diffusion gating, to work with high frequency light, we're going to place the sources pretty close to each other. This is the first thing that I want you to appreciate, that to have enough width between the X or fringe widths, we have to have the sources placed pretty close to each other. This is one factor. There is a secondary factor. The secondary factor is that if you remember the way diffraction happens in a certain space, let's say I'm going to draw a barrier and try to explain this part. Let's say if this is a physical barrier, let me fill this up with black maybe, and then get off certain space, make my point. Let's say this is a certain amount of gap that there exists at the center of a certain barrier. I'm only showing one gap to make my point. What you have learned in your O levels, that if the wavelength of the incoming waves, which are supposed to be parallel to this barrier line, this is equal to the gap size. So if this is the scenario, I mean, as close these two things are, lambda and the gap opening size are, we're gonna end up with really beautiful circular wave pattern, or the diffraction is gonna have a really wide angle. Really wide angle means it's gonna diffract in a pretty large angle from the center. So it will be really highly diffracted, which means you have a large spreading. This spreading effect goes down, or this large angle of spreading actually become reduced whenever these two measurements, let's say lambda, and let's say I'm gonna say this gap as, let's say, G, that lambda and G size, they become somewhat mismatched. Mismatched in this case, I mean that if lambda is big, G is small, in that case also we're gonna have less diffraction. If lambda is too small, if the lambda is too big and G is too small, we're also gonna have less diffraction. This is the best case of diffraction, where you have the most wide circular shape wave pattern. So this is one part. The other two variations that I want you to appreciate is that if we have the similar scenario, where the incoming wave fronts are significantly smaller, the wavelength is significantly smaller compared to the gap size, or the gap is really way too big, what happens then? So if I try to draw multiple waves which are pretty close to each other, representing that they have a very small wavelength, so let's say these two things, and then another one. Drawing three, at least three is good, so that you can see a consistent behavior of wavelength. So you can see over here that the wavelength is actually quite small. So let's say this is the wavelength of the incoming wave, and this much is the gap size. So the gap size in this case is extremely large compared to the wavelength. So what's going to happen through this flat part or through this opening, identical shape of wave is going to go through, and we're going to have a little bit of diffraction on their sides. Just to save me from the trouble of drawing this whole thing meticulously, I'm going to copy this part and do a little bit of stuff for myself. So let's say one thing is over here, the other is over here, the other is over here, something like that. So through the flat part or through the big opening, the flat waves are still gonna come out as flat. There is gonna be no observable bending or curve whatsoever. Exclusively from the sides, we're gonna see some amount of curvature. So that's I'm drawing by green to give a bit of an idea that how much bending should we expect. Pretty small. We're gonna have a bit of a curve, and all of these curves are gonna have their center at this corner. Is in this corner they're gonna be having centered. No, so they're gonna have this kind of shape. And over here, if you consider that the how much bending did this wave actually do, this is the actual angle of diffraction that we can talk about. The original wave of the duration of the wave was this much. Maximum amount of angle that you could get is this much. So it's not that high. So the waves are not that much diffracted. So they are not bending as much as you want. And also the third case is that if we have two waves, if we have the pairing, this whole thing is going to happen on the bottom side as well. Don't get the wrong, at the bottom side will not happen. I just didn't draw it because I wanted to save some time. The third possible scenario that we can have can look like this. Let's say we have a barrier right up here. Let's fill this up. And then if the gap is extremely small compared to the, not extremely small, significantly small compared to the wavelength size. So let's say this is the gap size, and if we have wavelengths of about, let's say, this much big. So we have pretty big wavelengths over here compared to the gap sizes. So if this is a scenario, there is a scenario like this, what happens, the waves are still going to make the circular shape pretty much identical to the circular shape that we obtained over here. They are going to make circular shape, but their angle of spreading would be pretty small. So the way it works is that I'm not essentially sure exactly what works as a center. I would have to look about it. But typically it produces waves with small angle deviations. The wavelength essentially remains the same because I'm trying to represent over here that this medium and this medium are identical. So there shouldn't be any refraction effect. So the wavelength over here and the wavelength over here should be exactly same. But this amount of spreading would be significantly small. You're not going to have as much angle of curve as the first figure that we have had. But still, all of these wavefronts are going to be quite circular, or as circular arcs. But your angle of diffraction is going to be pretty small. So it's not going to be spreading out as much. Why am I reminding you about all of this O-level stuffs? Because I want you to understand that to have the most amount of spreading, to have the biggest amount of diffraction, we need to achieve this. This is our optimum situation, and we need to have that. Whenever we're going to do our experiment with a high frequency light, the lambda of those light will be pretty small. So whenever the lambda of, I mean, whenever the lambda is pretty small, you to have a good amount of diffraction so that you can have the whole thing, whole keyboard screen pattern, bright and dark pattern over a large span of your screen, so that you can make better measurements. We would appreciate that our the hole size or the gap size of the barrier in the area through which the lights are going to come about, this gap size should be comparable in this case mean nearly equal, not like 10 times 20 times big, or not like 100 times or 200 times smaller. They should be comparable within so that this wavelength and this gap are pretty close to each other, which means we have to make this gap quite small if we're working with pretty high frequency light waves. Let's say purple. If you want to work with purple, exclusively purple monochromatic light, then this would come with a very small wavelength. To have a good amount of spreading, we would require this to be done by a small size gap. Now there comes another problem. The smaller this gap is going to be, less energy of light can actually pass through, because the bigger gap allows bigger amount of light to pass through, more space, more energy, and more vibration can paint it to the right side. The smaller this gap size is, less energy can pass through, which means to have a good diffraction, we have a small gap size, but making the gap size smaller will make the energy coming out to the right side is going to be pretty small as well, which will ultimately make the entire pattern very dull, very very less bright. So it wouldn't be difficult to observe once again. So we're running into the same problem, that the whole pattern becoming less bright. So how can we solve this problem? That's where the idea of diffusion getting comes in. The diffusion getting is basically a solid transparent object. For example, you can think of it as a regular glass block, which is going to be scribed in, it is going to be scratched by a specific mechanical device in a very precise way, in such a way that the diffraction getting, let's say, uh, a typical diffusion getting actually looks about this much, and there is a certain portion over here which has a bit of a shaded color. Maybe I can draw another rectangle over here with a bit of a shade color. Maybe let's say there is a slight shade that you can see over here, which is actually where the diffraction part is. Now, what is, if I try to draw a very highly magnified view of one small section of this part, let's say like a very highly magnified view. In this case, this circle is not, and these circles, they are not proportional. I mean, these are not drawn to scale. What exists within this part is that there are certain stripes of non-transparent lines, which are actually the scratches made by the mechanical part, and there are gaps between two lines. So these kind of lines are there. These lines are all parallel to each other, so not very much exactly the way I'm drawing, but they are equidistant and parallel lines. So if I try to draw this in a bit more civilized way, I might as well try to draw it with rectangles. So this is the phase view that I'm trying to show you. To do the experiment, we have to place the light source behind this thing, and the screen should be placed in front. So this is the phase view of this whole thing. So the way it works is that it has, actually, should I show this in this manner? No, I shouldn't be showing you in this manner. I'd rather show you this in a horizontal way, because, well, it's the same thing. It's just an anti-degree rotation. So so that whenever we'll pick this up, you can actually get less startled that how did this become rotate 90?
Sir,
Yes.
ওয়েভ গুলো তো ডিফ্র্যাক্ট করবে গ্যাপ দিয়ে, বাট ব্যারিয়ার দিয়ে কোনো ওয়েভ রিফ্র্যাক্ট করবে না?
No, those barriers are non-transparent. They are like, when those marked or sketched lines work as the barrier, and the gap between two barrier basically works as one small tiny source.
আচ্ছা, ঠিক আছে।
It's something like, if you think about it, if you think for our wooden fence, garden fence, I mean, there are planks of wood, and there is a gap, and there is another plank of wood, and there is another gap. Do you understand what I'm saying? Like basic garden fence.
Yes, sir.
I might as well, because it's just popped in my head. I'm happy that I can actually show you this, because that's exactly what happens. Yeah, that's exactly what exists within a diffraction grating. Exactly something like this that I'm talking about. not these things, the vertical fences that I'm talking about. Just forget about the horizontal support system. If you just look at this part, I mean, you can consider that one of these planks work as a barrier. I mean, if you're trying to shoot light through here, and if you hold up a screen over here, this much large gap wouldn't be give us any diffraction. But just to make sense of what is inside the diffraction grating, the structure of the diffraction grating, that there are parallel lines drawn with equal gaps. Interesting part is that it doesn't have to be, I mean, all of these lines are parallel. So all of these unscratched spaces, or where there was no scratches, these holes or these transparent locations work as your source through which the light can actually pass through and get diffracted. And all of these wooden planks or the scribes or the scratches on your on the glass, they work as your barrier. So practically speaking, we are going to have a lot of sources over here, one after another, one after another, stacked one onto another one. Not only two sources, we're going to have a lot of sources. If you wonder why, like I said, that we would appreciate the fringe to be quite bright. Now, if we want to have a quite bright enough fringe, we necessarily have to have more light. We cannot allow more light by allowing a single thick gap, because that would not give us much to diffraction. We require the gap size to be nearly equal to the wavelength size. So the individual gaps have to be small. But then again, if we want to make the fringes bright enough, we need to introduce more than two slits. So basically, by achieving this, we are actually introducing a lot of slits. So these slits are going to be over here. So that's the basic part of this discussion. এই ডিফিউশন গেটিং এর কোর্স স্ট্রাকচারটা বুঝা গেছে কিনা দেখো। এরপর আমি একটা ট্রায়াঙ্গেলে যাব, ট্রায়াঙ্গেলের একটা আইডিয়া বুঝাবো। ইয়েস, জারিফ, জারিফ, you raised your hand. Okay, I think maybe I have answered the question already. এই পর্যন্ত বুঝা গেছে সবার, সরি, এই পর্যন্ত বুঝা গেছে সবার ডিফ্রাকশন গ্রেডিং আমাদের কেন দরকার, মানে why we had to improve the double slit experiment into a new type of setup for diffusion getting. It's all because we want to work with a high frequency wave, and we want to have a good diffraction, and then again we want to have bright fringes. To accommodate all of this, we have to have individual slits which are going to be pretty small. We have to have multiple slits so that more light can pass through, thus we can get a bright enough fringe pattern. That's the basic idea. So if I just try to now show you the geometry for diffusion gating, I might as well pick up some figure from the net because it should be easier. This Khan Academy figure is pretty amazing, but I'd like to get something else. No, this is actually pretty amazing. I don't want a lens because the lens is not introduced in the syllabus, so I'm going to forget about the lens. Nice figure.
স্যার তাহলে এখানে সেন্ট্রাল ম্যাক্সিমাটা কোথায় হবে?
হ্যাঁ বলতেছি, just a second. সেন্ট্রাল ম্যাক্সিমাম একদম স্ট্রেট লাইন বরাবর হরিজন্টাল যে প্যাথওয়েতে আমাদের ওয়েভটা আসতেছিল, এক্স্যাক্টলি ওই প্যাথওয়ে বরাবরই আমাদের সেন্ট্রাল ম্যাক্সিমাম আসবে। আচ্ছা, এই ফিগারটাও বুঝাবো, এই ফিগারটাও তোমাদের লাগবে না, তারপর আমি কেন লাগবে না সেই জিনিসটাই বলবো জাস্ট। I'm actually choosing a lot of figures, might not as well use all of them, but I think this will work. Do I need more? No. Achha. Let me explain what are the figures that I just picked. So might as well go into this site to see what beautiful information they have. Diffusion Gettings. Okay, yeah, this is nice. So let's have a look at this figure. This is a well made figure. So I'll explain what is happening. Actually, before I get into the idea the macroscopic description of the idea, one thing that I would like to tell you is that for the diffusion getting mechanism to work for us appropriately, the way we set up the apparatus is that we have the diffusion getting over here. Let's say this is the diffusion getting. Somewhere in the middle, we have those slits. We send a monochromatic light horizontally. This is important. This line has to be horizontal. This doesn't look horizontal. Might as well make it horizontal. So let's say I'm drawing a horizontal line all through because I'll be using this thing as the incoming light, and this is supposed to be my central maxima line. So along this line, I'm going to have my central maxima. How the central maxima get produced, I'm going to discuss. Don't worry about that. And to accommodate the whole pattern, I mean, the reason because we have chosen hole size or the source or the slit size to be nearly comparable with the wavelength of the incoming light waves, the light waves actually spread out a lot, like a lot. So this whole pattern that we're going to get in this experiment is impossible to accommodate with a flat screen. So what we do, we use a semicircular screen, something like this. So it's a curved screen. Using the curved screen, we're going to measure angles. So we're not going to essentially measure distances over here. So the central maxima is going to be produced over here, which we usually label by n equals to 0. Why? What does this mean, n equals to 0? I'm going to talk about that. I mean, where does this n come from, or what is the significance of the n? Or you can essentially understand that n equals to 0 essentially means the path difference is 0. That also works, because that's basically what we showed in the double slit experiment as well, that for all the maximum points had a path difference of n lambda, and where the minimum points had a path difference of n plus half lambda. That was our key information. So n equals to 0 represents the location where the path difference is 0. If you wonder that path difference of what, I'm going to tell you about that. Just hold your horses. Then we're going to have n equals to 1 at certain point on the top, and we're going to have n equals to 1 at the bottom as well. This is supposed to be a perfect semicircle, but no, it's not. But it always works in such a way that the angle it produces on both sides are exactly equal. So if n equals to 1 is over here, if we have theta over here, you're going to have the same angle theta over here. There is a reason, which I'll explain, that the angle at which n equals to 1 is produced, n equals to 2 is usually produced at a much bigger angle compared to the double. So if let's say if this is 20°, this angle for, let's say this is theta 1, and let's say this is n equals to 2 on the top side, and this is, let's say, theta 2. You can see that all of these angles that I'm measuring, they're not the angle between the top and the bottom. All the angles are measured with respect to the central maxima. This is a very important information. You cannot have, I mean, this whole thing is not theta 1. Theta 1 is the angle of the first maxima, starting from the central maxima all the way to the position of that maxima. So this is theta 2. Now there's a reason why this increase happens. I'll talk about this a lot after a while, but I want you to understand that there are angles involved over here. Now comes a bit of approximation, and this approximation might actually bug you. It bugged me when I was a student, but this is the way this is explained. One of the part that I really want you to appreciate is that, let me pick up a figure. I'll take this figure. Open image in new tab. Can I get that exclusive image? No, this whole thing is a single image. Okay, let's take this image. Copy image. Let's paste it here. Okay. This is a highly magnified view, like a superbly highly magnified view of the diffusion grating. Here, they have labeled a certain term as E. For your syllabus, this term is not labeled as E, this term is labeled as D. So that's why I'm erasing this thing. This is the D. D is the diffraction grating constant. This is a term. I'm going to write this up. Diffraction grating constant. D, which can be also described as the sum of two quantities. Let's say D equals to A plus B. Now, if you wonder what A and B are, let me explain. In it, maybe which is on the right side. Let's say if this is our diffusion grating part, let's say this is the whole barrier, and we have a bit of gaps in between. Let's say this is a one size gap. Delete. and then let's say this is another gap, and let's say this is another gap. So I'm only drawing this much, although it doesn't look as much correct at all. I can actually try to increase this a little bit so that they appear to be identical. Okay, I think it works, and then a little bit missing over here. Okay, uh, why am I going through this troublesome step process to make it? What I want you to understand, if this is a diffusion grating, this is a hypothetical way or a graphical way to represent the existence of the diffusion grating. What this is trying to represent is that all of those rectangular hole spaces work as your source, individual tiny sources through which light waves can actually pass through and go on to the right side. And all of those black spaces represent the barriers through which the light waves cannot pass through. Now, if the individual hole size, let's say if this part is labeled as a measurement of A, these are usually come in nanometer measurement or maybe micrometer measurement because they are extremely small. They are made by very precision devices. And let's say the barrier size is labeled as B. Uh, the total sum of these two things is named as diffusion getting constant A plus B. The reason I am labeling this A plus B because I want you to understand that it is the sum of both of these dimensions gives you A plus B. One thing you need to understand, if you replicate this much, I mean, you're gonna get the same thing. So after B, you're gonna have another A and another B, and then another A and another B. So basically speaking, you are going to have, so this much part is basically one unique part of this diffusion getting. Every diffusion getting is made in such a way that all of those hole sizes have the same dimension and all of the barriers have the same dimension. If that is not happening, then we cannot produce a good pattern on the screen. We're not going to have a functional experiment with that equipment. So diffusion getting is always made with this thing. It is not essential that A and B have to be equal. For some equipment, they may be equal, but it is not essential they have to be equal. In most cases, they are not equal, but their sum is always maintained throughout the diffusion getting uniformly. So that's the idea for diffusion getting constant, which is going to be helpful for us after a while for calculation. But let me elaborate this idea a bit more. The typical way we are going to work with the term diffusion getting for our math is that we're going to have information like this. Let's say there in a diffusion getting, there are, let's say, 10,000 lines or 10,000 lines in 1 centimeter. So if there are 10,000 lines, it should also mean that there are 10,000 gaps, because you cannot have 10,000 lines and less gap, because like I said, it is the repetitive part of the diffusion getting. So how much is the diffusion getting for this thing? This question is only telling you that there are 10,000 lines in 1 centimeter for diffusion getting. It is made in that way. It is not saying what is the individual thickness of those lines. It is not telling you what is the individual thickness of those gaps. It is telling you that there are 10,000 of these lines, black spots in a diffusion getting. So this essentially means that the diffusion getting constant can be calculated by 1 centimeter, which I can write as 10 to the power minus 2 meter, because for calculation we'd preferably convert everything into meter SI units, divided by 10,000. So, sorry, should not have issued guys. Divided by 10,000. This is the value of your diffusion getting constant. So this is gonna be 10 to the power 4, so 10 to the power minus 6 meter. So for this question, this is the diffusion getting constant, which we will be eventually using for our math. So that's the idea for diffusion getting constant, which is actually the sum of these two quantities of gap length and the barrier length. Now coming back to this figure, I would like to take this figure a bit more empty space, so I might need a bit more space to work with it. Okay, here is good. One of the important things that I want all of you to understand, that this is a highly magnified view of a very small equipment. It means D comes in the scale of 10 to the power 6, 10 to the power minus 5. So 10 to the power minus 6, 10 to the power minus 5, that kind of measurement. So it means that this line, these dots are actually pretty close. compared to this distance, the location where the screen is actually located, what I mean is this much gap is actually quite significant. This gap could as well be half meter or 1 meter, something like that. The radius of this circular screen, this is gonna be pretty large. So for the sake of discussion, I want all of you kids to accept that we can consider this d value extremely small compared to the distance that the light rays have to travel to reach to one single point onto the screen. Can we appreciate that?
Yes, sir.
T is extremely small, like minusculely small compared to the length of the path that the light rays have to travel to meet at a point. So here they are showing us a certain figure. Okay, so let's say somewhere over here, I'm gonna draw a random break sign to represent that here we have squashed up some distance. Let's say this is the screen. This is the central maximum position of the screen. So here we're gonna have central maxima. The reason we're gonna have central maxima is because you have to understand one thing. Let's say if this is the this is the screen, and the central maxima is a one single spot on the screen, which is extremely bright. Let's say this is the position where the central maxima is located. All the individual light rays coming up from these individual sources should meet at this point with zero path difference. The generalization or the approximation means that something that we're considering to be true, and it's very close to true, but it's not essentially perfectly true. That's what we mean by approximation. For example, we approximate decimal numbers all the times. So it's not exactly that, but it's near to that. So the approximation is that because this distance is extremely long, and so if you consider the lights coming from 1, 2, 3, 4, these 5 sources all the way to this central maximum point onto the screen, these light rays are definitely gonna have some angle in between them. So if I just convolute this figure a little bit to make sense with what I'm trying to mean, this is a white line, so cannot be seen. So let's say if one light ray comes from this source to this point, and another light ray comes from this point to this this source to this point, and this one this. Geometrically, if you consider, it is impossible that these 3 lines would be of equal length. Is it possible? To very high precision value, they are not essentially equal. But because this distance is extremely small and this distance is extremely large, we can consider these lines to be nearly equal. That's one approximation that we're dealing with, that whenever we are considering light rays going this way, we are going to consider for the central maxima, the path covered by the individual light waves from the diffraction grating are all equal. If you wonder that why this approximation is actually logical, I'll show you this. If you consider the original figure, this is a diffraction grating, which is illuminated from a single point light source, very sharp light. So typically we use laser of a monochromatic laser to illuminate the diffraction grating. A very small location on the whole diffraction grating is going to be limited. We're not going to even illuminate this entire part of the diffraction grating, which has all the hash marks. Why did I draw this? Where ছিলাম জানো? হারিয়ে গেছে? Rectangular ছিল না কোথায় জানো? আচ্ছা, never mind. So we're not even using the entire part of the diffusion getting where the sketches are. We are actually limiting a very small section of this thing. So the radius of this, or the radius, or so you can say diameter as well, of this light beam that is falling onto the diffusion getting is extremely small. So from this small distance, from multiple different holes in this location, which are really close to each other, a group of light rays are going to fall at this point. So for practical reasons, we can consider that the path difference is 0. Are we okay with that? Polaban.
Yes, sir.
এই জেনারেশন থেকে বুঝছো সবাই যে এটাকে আমরা 0 হিসেবে ডিফাইন করতে পারতেছি কেন? Because at this point we're going to have central maxima. This is the one approximation that we have. The second approximation is that if I actually draw the physical lines from here to here, these lines are actually appearing to have some pretty sharp acute angle between them, because I have not drawn this figure to scale. But if this thing was actually drawn to scale, I mean, if these lines were actually drawn with appropriate scale, and the diffusion and the screen was actually placed with scale of this one, the screen would be, let's say, for this figure, the screen would be, let's say, half a kilometer away from this point. It's going to be really far away if this whole thing was magnified up to scale. And in that case, if you actually drew all of these lines would practically appear to be parallel with each other, because these are a very small section of very long converging lines. These lines are actually converging onto this point. These lines are actually converging onto this point. There is no doubt about that, because other than that, you cannot have superposition. The requirement for a superposition or interference to happen is that multiple lights from multiple sources have to meet in a single at a specific location at the same time, and together they will produce a combined effect. So you have to have light rays converging to have this thing. But because these light rays are meeting at a really far away point compared to the scale of this figure, for these lines are actually not appropriately drawn. These dotted lines more or less represent those lights' actual pathway. So for practical reasons, we can say that these lines are nearly parallel to each other, these dotted lines. Can we agree on this information as well, that light rays would be parallel?
Yes,
Yes,
sir.
sir.
Not essentially 100% parallel, but the angle between them might be as well be maybe, let's say, 0.00. I mean, you are going to have a lot of zeros after the decimal point, and then some digit shows up, that many degrees of angle between those light rays. So for practical purposes, we are doing two things. Number one is that we are considering that the path difference of all of these light rays meeting at the central maxima is practically 0, which is giving us the central maxima where all the light rays are covering the same length of path. And second thing is that we're considering all the light rays which are eventually coming up from here and eventually meet on point on the screen. These light rays can be considered to be parallel. This is a generalization or approximation which I felt really bugged, and I could not accept this for a very long time. Then my teacher convinced me that we are doing this because this is logically acceptable. So there is a thing that is true, and there is a thing that is close to true, and that is functional. So we do use that. For example, there are people who are good and there are people who are less good, but we make the society with all of them. Anyway, I would like to get rid of this figure. Should I get rid of these things, or should I get a new figure? I might as well copy the figure again. This can stay somewhere over here. I don't mind. I'm gonna copy the figure once again. Okay. So what I want you to understand is that for this figure, these dotted lines represent the position of the central maxima. Let's assume that these, you have to understand this thing, that if you consider this light source, light rays from each of these sources are actually spreading out in all directions. For the sake of our discussion, we are going to pick up one set of light rays and observe them and discuss about them. That can lead us to a definite decision. Let's say at any instant we are considering these light waves, which are all actually these light waves which are all going parallel to each other onto this thing, and ultimately down into the, I'm going to give a break sign to represent there is a squash of space, and ultimately on the screen all of these light rays are going to meet on a single point on the screen. Let's say this point where these light rays are meeting is n equals to 1. Having n equals to 1 would essentially mean that all of the light rays which are merging over here, they are, each of them are 1 lambda path difference apart from each other. N equals to 1 means path difference is 1 lambda. So what would this mean? Have a look. If you consider, I mean, if you have a look, let's say, consider this blue line, this one. Consider this blue line. You should see that the total path from this blue line all the way down to the margin point, I mean, this whole part is equal for both of them. So let me name this source. Let's say source 1, source 2, 3, 4, 5. So I want all of you to understand that the instant the wave from source 5 is produced, source 4 produced that merging wave a bit earlier, and when the wave from the source 4 reached to this point, the wave from source 5 was produced so that both of these lights could travel together and eventually merge on this point. So essentially, the path difference between source 4 and 5 should be 1 lambda, which brings me the idea. Let me choose a bit small thickness. So this would mean that this much extra path that the light ray from source 4 had to cover has to be 1 lambda. If this is 1 lambda, this entire thing is 1 lambda as well. Similarly, the path difference from source 4 to source 3 is also 1 lambda. Because like I said, that each of the individual n equals to 1 is being at such a point means all the waves, individual waves which got merged at this point are 1 lambda apart in path difference from each other. Each of them are. So this is 1 lambda and this is 1 lambda lambda. They have used theta part to pore boltesi, and this is also 1 lambda as well. So you can see that if I just try to give you a bit more idea, the path difference between source 5 and 4 is 1 lambda. Path difference between source 5 and 3 is 2 lambda. Path difference between source 5 and 2 is 3 lambda. Path difference between source 5 and 1 is 4 lambda. Here you can see 4 lambda. You see 1 lambda, 2 lambda, 3 lambda, and 4 lambda. So which means you have a full multiple variation of path difference among the sources, which means you're going to have merge of all the crests together. But some crests were produced earlier, some crests were produced later. But consecutive sources have a path difference of 1 lambda. That's the important bit, consecutive. I did not say the word consecutive up till now because I wanted to explain this in this figure. So you can see that if you consider any random two sources, they don't have essentially have a path difference of lambda, but they all have a path difference of a full lambda multiple, because other than that you cannot have the same phase merging and you cannot have a constructive interference leading to a bright fringe. To have a bright fringe, it is imperative that we have the same phase merging. So consecutive sources have a path difference of 1 lambda, whereas any two sources have a phase difference of a full multiple of lambda. This is what is achievable at n equals to 1. The reason they are showing this angle theta over here is this, that let me, if I draw the bigger picture over here with a small effort, let's say this is our n equals to 0 position, and let's say down over here, let's say this is our n equals to 1 position. This is the angle that we call to be theta. Am I correct?
Yes, sir.
That's what I told you a bit
Yes,
earlier.
sir.
So
Yes, sir.
you can see over here, they have labeled theta over here, another theta over here. They are trying to show you that this angle is theta, or maybe this angle is theta. So this group of light rays, which are drawn as these things, which are actually going and meeting onto the n equals to 1 point onto the screen, these light rays are making as a group, or each of them are making an angle of theta with the central maxima line or with the horizontal line for this figure. Now we have this figure and we have this triangle. Now I want all of you to take a very good look and bear with me for this part of the figure. I'm going to expand this figure and I'll ask you some questions for you to answer. Take a good look. Let me use green. Take a very good look. This is a right angle triangle. Do all of you see it?
Yes, sir.
It doesn't have to be
Yes,
isosceles.
sir.
It appeared to be isosceles over here, maybe because of the scale of the diagram, but this is isosceles. Here, this dimension is labeled as D. So this is a right angle triangle. So remember this part. Here the path difference, because I was discussing about D, n equals to 1 to make easier sense for you to understand. Here the path difference is lambda. Okay. Let's say if this path difference is not lambda, let's say if we want to represent this path difference as, let's say, path difference, I'm going to write this as path difference. So let me give it a random name. Let's say I'm going to name it, what should I call it? X? No, X is something else. Let's say I'm going to name it Y, just a random variable. We are going to replace this variable. It's not going to be permanent for us. I want to express this Y in terms of D using this angle theta. So have a look what is happening. If this is a right angle triangle, it is obvious that red, this is also a right angle triangle, right? Keep observing.
Yes, sir.
This angle is theta. So as opposite angle, this one should also be theta, right?
Yes,
Yes,
sir.
sir.
So how much is this angle? This one, how much is this angle? 90 minus theta?
G,
This
sir.
is a right angle. So how much would this angle be? Theta?
Theta.
This is one way to go around. So I just took one way because they have labeled a theta over here. Another easier way might as well have been if I just rub off this figure over here, the easier way might as well can be that this angle was theta, so this is 90 minus theta because this is 90 degree, so this is also a theta, so you could also go from here as well. But we can say that in this right angle triangle, this angle is theta. So if I just try to draw this angle, a triangle right over here with a bit of a fair view. So here we have the 90 degree, this is our D and this is our theta. So if this is the case, what should be the, and I label this side as Y, which was my path difference. Y equals to D sin theta hobe na?
Yes, sir.
Take a look, this is the opposite side of the angle. Y equals to d sin theta, which means d sin theta is always your path difference, no matter what. So I can tell you, although this figure is actually quite convoluted, again, if I take this clear figure, I can tell you that for this figure, if we go for any random angle, not essentially for n equals to 1, if the multiple rays would meet at a certain point on the screen, which is happening every single instance, each of this part, this one is d sin theta, 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 this one is d sin theta. So in all of these cases for the diffusion grating, the path difference is expressed as d sin theta, and that's where the all the magic happens. So I can now predicate that for the what is this thing called, diffusion grating, the path difference equals to d sin theta, and from here on I can actually derive everything. So if d sin theta equals to n lambda, where n equals to 0, 1, 2, 3, dot, 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 they will all give us bright fringes, and this is equally acceptable on either side of the central maxima. Either side of the central maxima. So which means এখানে আমাদের theta angle যেই theta angle n equals to 1 হবে, উপরেও আমাদের equal theta angle n equals to 1 পাওয়া যাবে. This is a bisymmetric orientation, and theta is always made from central maxima. তোমাদের সিলেবাসে for some reasons শুধু এই ফর্মুলাটাই আছে. Whereas in my opinion, which I always prefer to teach, that if we know that this is the expression for the bright fringes, can you please guess what should be the expression for the dark fringes? What should I write over here?
Equals
In lambda plus lambda by
half.
2.
Beautiful. N lambda plus lambda by 2 is basically this, n plus half lambda, yes. So, and the expressed value of n pretty much remains the same, 0, 1, 2, 3, blah, 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 blah. So this is supposed to be the logic for the dark fringes, but for some reasons, I don't know why, in your syllabus, they don't teach you this formula. They only work with the bright fringes and bright fringes only. I don't mind, because that's what I have to do. I cannot mind. So this is the formula, key formula for our diffusion rating. A quick recap. D is the diffusion getting constant. Theta is the angle at which that diffusion bright fringe was produced. N is the number of path difference between two consecutive slits of the diffusion grating, and lambda is the wavelength of the source. So that's how we work, and there are a couple of more things to describe from this diffusion grating discussion, which is going to be helpful for you in the long run. But before I move on, are we clear and of what we just discussed about this whole thing? এই পর্যন্ত বুঝা গেছে কিনা সবার clearly?
Sir,
জি,
sir, diffraction grading আপনি একটু আগে calculate করলেন না যে 10 to the power minus 2 meter divided by, হ্যাঁ স্যার এটা পার্টটা আরেকবার বুঝাবেন।
কোশ্চেনে আমাদেরকে দেখো, এখানে আমাদের ফর্মুলাতে তো ভ্যারিয়েবল আছে মোট 4টা, d, theta, n আর lambda, তাই না? So we have 4 variables over here, which means if the question somehow gives access to us any of the 3, we should be able to calculate the 4th. So in many cases, we are asked to calculate theta, n, or lambda. In many cases, we are also asked to calculate the d. But if in any question, the d is supposed to be given from the formula, they don't usually give you the d value directly in meter. They rather give you this set of information, that diffusion getting is such that there are 10,000 lines in 1 centimeter, or maybe they will say 2,000 lines in 1 centimeter, or maybe they will say 3,500 lines in 1 centimeter. It can come in any different form. So if there are these many lines, this necessarily means there are equal number of gaps as well. So these many lines necessarily mean these things. These are the lines. but lines would not be created without the presence of gaps in between, because that's the structure of diffusion grading. So if you have 10,000, for example, if this much is 1 centimeter and there are 10,000 lines within this 1 centimeter space, there are equal number of gaps within the space. The reason is that, I mean, if you start to observe from a line, you should have a gap afterwards, right? You should have a gap afterwards, and
जी
then you
sir.
should have another line. Oops. Then you should have another line, and you should have another gap. So which means at the end of your 1 centimeter line, it should finish in such a way that you should observe one line, and then you should finish your observation after one gap, and then there might be another line over here. But the point I'm trying to make, that your 1 centimeter measurement will start exactly from the top of this line and finishes at the bottom of this gap. This is 1 centimeter, within which you have exactly 10,000 lines, which essentially means there are 10,000 gaps as well. So the way we can calculate the value of D is simply divide that length measurement by the number of lines, and that gives you the D value.
अच्छा sir.
বুঝা গেছে?
जी sir, বুঝেছি. Thank you sir.
Sure. আচ্ছা, এটা গেল। Additional যে জিনিসগুলো আমি বলতে যাচ্ছিলাম সেটা হচ্ছে, there are two different words the question seem to ploy with the students' mind if they're not careful. Is that I'm writing two expressions over here. Each of these n thing that I have used as n for the figure, let's say n equals to 1, n equals to 2. This n is, for the diffusion, is also called the order of maxima. Order of maxima. So one way, this is just another way of expression. This is what we call the central maxima. Then we can call first order maxima, You see, this is not second order maxima. This is also first order maxima, because like I said, they are symmetric on top and bottom with respect to the central line. So this is first order maxima. Then you can have second order maxima. Similarly, you can have a second order maxima over here, and so on and so forth. So this is also called the order of maxima. Now, interestingly, let's say in a question, they ask you to calculate, what is the, before I go forward, from the figure, by observing this, any of this figure, let's say if you just observe this figure, what is the possible maximum value for the theta? For example, if I write the equation over here, d sin theta equals to n lambda, what is the maximum possible value for theta for this equation? Observe this figure and try to have a guess. Possible maximum value.
Possible maximum.
Yes.
$89.
So you're proposing something less of 90. So you're assuming it shouldn't be 90, right?
Yes,
Ji,
sir.
sir.
Okay. The thing is, we consider it to be 90. The reason we consider it to be 90 is that we are assuming that we're going to have the wavelength and the gaps matched up so close that light would be able to diffract even at 90 degrees. So the reason I said possible maximum, we usually use, I totally appreciate your line of thinking. That's exactly what I was trying to get at. But the maximum value for theta, for calculation purposes, we use as 90 degrees. This is the maximum value of theta that we use. Because light cannot, by no means light can bend beyond the alignment of this diffusion getting. That's not going to happen. The maximum it can bend is 90 degrees. So কখনো কোনো যদি এরকম কোশ্চেন হয়, লেটস সে আমি একটা স্যাম্পল কোশ্চেনই ধরো এখানে যদি করি যে I can actually pick up one question from the MCQ paper and try to solve it rather than making up a question. Give me a bit of a time. Let me find out one question. This is double slit experiment, exclusive. This is a diffusion grading. Okay. Take a look at question number 8. A A diffusion getting with 500 lines per millimeter is used to observe the diffraction of monochromatic light of wavelength 600 nanometer. Okay, good. The light is passed through a narrow slit, and the grating is placed so that its lines are parallel to the slit. Light passes through the slit and then the grating. An observer views the slit through the grating at different angles, moving through Y. To the grating through Y. Moving his head from X parallel to Z, parallel to the grating through Y, opposite to the slit, to Z, parallel to the grating on the opposite side. How many images of the slit does he see? So the simple question is that consider this as a top view of the setup. Consider this as the top view of the setup, which means this is let's say there is a table under below this setup which you cannot see. Our light is coming. We have a single narrow slit to not have a too much big wide vivid source, so that makes a bit of a difficulties. And now we have placed a diffusion getting over here, and this person is over here, and he is gonna move around, walk around, and try to see how many of this source can he see by moving around. I mean, if you wonder what does this even mean, this means that in places where the bright fringes of the maximas are, he should be able to see this source. Definitely he's gonna see it more bright at this position, and if he moves over here, he's gonna see it in some other position, and he's gonna move in other position. So if he moves all the way from this position over here while looking at the diffusion grating, each of the positions where there is supposed to be a maxima, this person should be able to see an image of that original light source, not the light source of the slit, of the primary slit, first slit. The question in this case is, how many of these images will this person be able to see? কোশ্চেনটা কি বুঝা গেছে? সলিউশন আমি বলতেছি, বাট কোশ্চেনটা বুঝা গেছে কিনা দেখো।
Yes, sir. Sir, আপনার ভয়েসটা
sir.
কিরকম জানি আসছে?
হ্যাঁ, কারণ আমি এসি অন করার জন্য একটু চেয়ার থেকে উঠছিলাম। It should be okay now. So এই কোশ্চেনটা আমরা কিভাবে সলভ করতে পারি? So let's take this question and break it apart. So what are the things that we want to understand that in this case the person is going to move all around. So the possible angle for the diffraction for the light to happen can be all the way up to 90 degrees. So if I try to solve this, in this case I can find out that my D value would be 1 millimeter divided by 500, that is 10 to the minus 3 divided by 500. এটা কত আসে দেখো তো? আচ্ছা, কিছু একটা আসবে, যাই হোক আমি এটা লিখতেছি না, লেখার দরকার না, একবার ক্যালকুলেটরে বসালে হবে। And if I now go for the equation D sin theta equals to n lambda, I'm trying to find out the value of n. So if I replace all these values over here, 10 to the minus 3 divided by 500, which is the value of D, theta is placed as a maximum value, which is 90 degrees, sin 90. This should be equals to n lambda. N is the unknown that I want to find out, and lambda is given over here, which is 600 nanometer. So 600 into 10 to the power minus nano koto 9. হ্যাঁ, সো এটাকে যদি আমরা সলভ করি, এখান থেকে আমরা n এর ভ্যালুটা বাই করতে পারবো। n এর ভ্যালুটা বাই করো, সবাই ক্যালকুলেটর প্লেস করো। I'll also do in my own calculator, find out a value of this thing. Sin 90 is 1, so that should be easy.
Sir, 3.3 into 10 to the power minus 18.
এত তো হওয়ার কথা না, শুধু
3 would 1 by 3.
3.33 দিয়ে আসে আমার,
Yeah, 3 or 1 by 3.
মানে ডেসিমেল এরকম আসে। যারা তুমি এখানে পাওয়ারে ঝামেলা করছো, 10 এর মাল্টিপলে ঝামেলা করছো, ভালো করে দেখো ওই ঝামেলা করছো। You got the 3 right, but somehow you messed up. This is the value of n. Now remember, n was named as the order of maxima. n equals to 3, এই কথাটার physical significance টা আমি তোমাদেরকে বুঝাই। এই কথাটার physical significance হচ্ছে this person will be able to see 3 bright fringes on either side of the central maxima. So if I just try to draw up over here, maybe with blue, This is gonna be n equals to 0. This will be present for all diffusion getting whatsoever. This person is gonna be able to see n equals to 1 over here. She's gonna be present to he's gonna be able to see n equals to 2 over here. He's also gonna be see the image as n equals to 3 over here. But this person is not gonna be seeing n equals to 4 because the maximum he is gonna be see is up to 3 point something. If this fraction was also bigger than 3.5, let's say if this was also 3.8, this would also mean that he would be able to see up to the third maxima, but the fourth maxima would not be visible. Do you get my point?
স্যার
Yes, sir.
0.8টা কি হবে?
Sorry?
এই 3.8 এর মানে 0.8 পার্টটা কি হবে?
আচ্ছা, এটা আমি জাস্ট বানায় লিখছি, বলতেছি যে এখানে তো তোমার n equals to 3.33 রয়েছে। সো আমরা যদি এটাকে অ্যারিথমেটিক্যালি রাউন্ড অফ করি তাহলে আমরা মানে 1sf করলে আমরা 3 পাচ্ছি, সেটা সমস্যা না। বাট যদি কোনো একটা সার্টেন ক্যালকুলেশন মনে করো 3.8 আসলো, ঠিক আছে, এখন 3.8 কে আমরা রাউন্ড অফ করে আমরা এটাকে 4 বানাইতে পারবো না। This would be wrong for this process. Having a fraction of 3.8, let's say n এর ভ্যালু যদি কোনো একটা ক্যালকুলেশন 3.8 আসতো, this would mean that the person is able to see up to the third maxima, but the person is not seeing fourth maxima, which means the acceptable value for n, the maximum order of visible maximum number of order of the visible maxima is still 3. You could not see, or the person could not see 4. You cannot do mathematical rounding for this math. That's what I'm trying to get at.
আচ্ছা
বুঝছো?
স্যার পার্সনটা কি
হ্যাঁ,
পার্সনটা কি স্লিটের ইমেজ দেখবে নাকি লাইটটা যেখান থেকে রিফ্লেক্ট করে আসছে ওইটার ইমেজ দেখবে?
this person is gonna see exactly how this slit looks like. If in this slit they place a small letter, let's say A or B, this person would be able to see A or B, that letter while they are looking at the bright fringe, because that bright fringe would be a perfect image of this thing. So however this slit looks like over here, they should be able to see that exact thing, but definitely with a decreasing order of brightness. The most bright image would be seen here, decrease. বুঝা গেছে?
Yes, sir.
আচ্ছা
জি স্যার।
আচ্ছা, এখন ফার্দার যে জিনিসটা আলাপ করতে যাচ্ছিলাম, এটা হচ্ছে একটা অ্যাসপেক্ট আলাপ করলাম, এটা ম্যাথসের জন্য একটা ইম্পর্টেন্ট অ্যাসপেক্ট, এটা আমাদের পেপার 2 করার সময় অ্যাকচুয়ালি সবখানেই লাগে, এটা এমসিকিউ তে লাগে, পেপার 2 তে লাগে। সেটা হচ্ছে ইউ হ্যাভ টু আন্ডারস্ট্যান্ড দ্য ম্যাক্সিমাম অর্ডার অফ ব্রাইটনেস ইজ 3. So should this correct answer be 3 for this question? For some student, they would gonna just simply calculate this and they're directly gonna go label A as the correct answer, and this is gonna be wrong. Have a read at the question. This person is gonna move all the way along this whole thing. So how many images of the slit does he see? So altogether, how many images is the person gonna see?
6
Almost.
4.
No,
something more than 6, তাই না স্যার?
it's one more than 6.
7
Well, there is only one option. There is one more than 6. That is 7. But guess why is
কিন্তু
that?
কেন স্যার?
This person is gonna definitely see the central maxima. This is a default one. He's gonna see 3 on top, 3 on the bottom. So total how many?
7.
7 আচ্ছা স্যার বুঝেছি। স্যার এখানে
বলো।
উপরে যে তিনটার মধ্যে কি x কেও আমরা ইনক্লুড করেছি না?
বলো, বুঝি নাই। তিনটার মধ্যে?
স্যার তিনটার মধ্যে তো x ও তো আছে তাই না?
Which one is X? এটা?
স্যার না স্যার এই যে মানে যে লাইনটা দেখিয়ে রেখেছে ওরা, এটা না স্যার, উপরেরটা।
এটা?
জি স্যার।
হ্যাঁ, মানে we are gonna see 3 bright fringes above the central maxima. Try to get the point. N equals to 3 means you're gonna see up to n equals to 3. So he's gonna see 3 above, 3 below, and he's gonna obviously see the central one. So he's gonna see a total of 7 images of this thing. So the question was asked that how many of the images is seen, or this question could also be asked in a different way, that let's say the person was not involved there, we only kept a single circular screen over here. Maybe I draw with a bit dark purple. So let's say we have a circular screen over here, and the question is asked that how many bright fringes are produced? How many bright fringes are produced? That answer will also be 7. How many bright fringes are produced? Alternately, this is one question, but if they asked What is the maximum order of the bright fringe that is produced? আমি দুইটা কোশ্চেন এখানে লিখতেছি, দুইটা কোশ্চেনের ডিফারেন্স বুঝো। একটা কোশ্চেন হচ্ছে how many bright fringes are produced, and the next one is what is the maximum order fringe that is produced. এই দুইটা কোশ্চেনের ডিফারেন্স বুঝতেছো? এই সেম কোশ্চেনের জন্য এই কোশ্চেনের আনসার হচ্ছে 3, এই কোশ্চেনের আনসার হচ্ছে 7. Check this out. Try to appreciate this information. If you have any question, you ask me.
স্যার স্যার নিচের কোশ্চেনের অ্যানসারটা 4 হইতো না?
What is the maximum order fringe that is produced? Which means what is the maximum value of n that was obtainable in this experiment? They're asking for the absolute value of n. They're not saying altogether how many bright fringes were produced. বুঝছো কি বলছি?
স্যার এখানে তো n0 আছে, n1 আছে, n2 আছে, n3 আছে, তো 4টা হয় না?
তারপর
তারপর তো দেখা যাচ্ছে না।
Okay, so what is your question?
স্যার তাহলে কি মানে 4 অ্যানসার কি হতো? 4 হইতো না স্যার, 3 কেন হবে?
পড়ো এই কোশ্চেনটা কি বলছে। What is the maximum order fringe that is produced? Maximum order fringe that is produced means what is the highest value of n that was obtained from the experiment? N equals to 0 is a default output for any experiment. Irrespective, you are always going to get the central maxima. Always. Above that, what is the maximum number of fringes? N equals to 1, 2, 3, 4, 5, 6 in that order. What is the maximum order that was obtained? This is, I mean, it's not that this is 1, 2, 3, 4. It's 0, 1, 2, 3. বুঝছো কি বলতেছি?
বুঝেছি স্যার।
This is 0, 1, 2, 3. And 0, 1, 2, 3 on the bottom side, there should be 3 more as well. So if the question asks that how many, then this would be the number of fringes multiplied by 2, because this would be symmetric on top and bottom side, plus the central maxima, which is 1. So this would be that. And if the question asks us what is the maximum order fringe that is produced, that would be only the value of that n. But you cannot essentially do the mathematical arrangement, you just have to take the integer value. Another typical example that I also tell the students in this case, which is not very related, but makes good sense, is that if you can, if you calculate up a certain sitting space for a car and volume of identical people, and if you find out that you can fit up, let's say 4.8 people in the car, you cannot actually fill up 4.8 people. You can actually fill up 4 people, because it is not logical to cut up a person to 80% and fill up into the car. I mean, that's not a person anymore, it's a corpse. So something like that. Do you understand what I just said?
Yes sir.
Okay, I hope that makes sense.
Yes, bro. Answer.
হ্যাঁ বুঝি নাই বলো।
না স্যার, হ্যাঁ ঠিক আছে।
আচ্ছা, আরেকটা জিনিস যেটা আমি আমার লেকচারের মাঝখানে স্কিপ করে গেছিলাম, আমি বলছিলাম যে আমি একটু পরে বলবো। আচ্ছা, বিফোর আই গো ফর দ্যাট, এই ডিসকাশনটা কি সবার বুঝা গেছে? কারো কনফিউশন থাকলে বলো, বিকজ দিস ইজ এ পয়েন্ট অফ কনফিউশন for this chapter. This is a very significant point of confusion to be able to distinguish between these two questions. They are not very difficult, but if you're not careful to look out for what you are answering for, you might as well mess up a bit. The next thing that I would like to discuss, which I said halfway, is that, okay, hey, this is the part. I told you that whenever the value of n increases, it increases in an increasing order. মানে হচ্ছে, if your theta 1 is produced at, let's say, 15 degree, your theta 2 is always produced at an angle more than 30 degree. So you'll get more than double. And if your theta 2 is, let's say, 31 degree, let's say, then your theta 3 will be produced at a value more than 62 degree. You are always gonna have increasing gap. Sorry, not essentially 62 degree. I mean, this angle is gonna be small, this will be even bigger, this will be even bigger, and so on and so forth. So if I just try to show you this thing for a drawn figure, diffusion grating, pattern. Yeah. কি ব্যাপার খুঁজে পাওয়া যাচ্ছে না কেন? বইয়ের ফিগারগুলো দেখলে অনেক জোস লাগে। These are nice. আচ্ছা, I should not get carried away. I should not get carried away. আচ্ছা, এটা তো মানে তোমাদের বইয়ের থেকে খুঁজে বাই করতে, তোমরা বই পিডিএফ বাই করি। এখানে পাইতেছি না কোথাও ওই ফিগার যেটা দেখা যাচ্ছে। হোল্ড আপ, এখানে ওয়েভস আছে কোন চ্যাপ্টারে? ওয়েভস আছে হচ্ছে 114। Okay, this was a good figure that I discussed the other day. We're gonna move this pipe to change the column height of the air column. Yeah, this is a much better representation for that experiment. Here we have this.
স্যার একটা কোয়েশ্চেন ছিল, সার্কুলার কেন ইউজ করা হয়?
Sorry?
সার্কুলার স্ক্রিন
Circular screen use করার কারণ হচ্ছে the diffracted light rays bend out at such high angle because we almost match up the wavelength and the hole size for the diffusion grating, that the whole pattern is quite impossible to accommodate in a flat screen. For example, let's say if this is your zero order and your first order is produced at, let's say, 30 degree, and if you place it at 1 meter distance, then you're gonna need sine 30. You're not gonna need at least 1 meter long of a screen to see these two patterns. And in that case also, you're gonna miss out the second and the third order. You're not gonna be able to see these things. If this angle is about, let's say, close to 70 degree, if you only want to see this third order spectrum in a vertical screen, your screen have to be extremely long, and the brightness of the third order will be very difficult to observe because it will be produced at a very high distance, far away distance. Because the spreading is more wide, that's why we prefer to use a circular screen. বুঝছো?
Yes, sir.
আচ্ছা, এই যে আমি এই ফিগারটা দেখাতে যাচ্ছি, এটা if you just have a look at this figure, although they haven't labeled anything, I'm going to give you a reason for this. You should be able to see that. Actually, let me zoom on it a little bit more. You should be able to see that this angle is of some value, but this angle is slightly bigger, and this angle is even bigger. Do you see that angles, the in between angles is getting bigger slowly.
Yes, sir.
Can everybody see that? ঠিক আছে?
in between
হ্যাঁ, এটা কেন হয়, এটা কেন হয় সেই রিজনিংটা আমি একটু আলাপ করতে যাচ্ছি, why that angle slowly gets bigger. So let me show you this thing. The equation goes like this: d sin theta equals to n lambda. So in this case, if I just take out the value of sin theta, it's gonna be n lambda by d, and what was I about to show you? Oh yes, if I
এটা
try to
কেন বড় হয়ে যাচ্ছে?
figure out the দ্বারা বলতেছি, if I try to take out this value of theta, this is gonna be sin inverse n lambda by d. হ্যাঁ, এখন ঠিক আছে। এখানে একটা জিনিস খেয়াল করো, theta is given by the sin inverse of n lambda by d, so which means other than drawing typically what is the trigonometric drawing that we do? Let's say if I trying to draw a graph, we usually draw a graph like this, sin theta versus theta, ঠিক না? So that if I want to draw it only up to 90 degree, we get a graph like this up to 90 degree. এখানে হচ্ছে 1। এখন আমি যদি এই গ্রাফটাকে উল্টায় দিই, let's say if I want to reverse those two axes, so that in this case the sin theta part becomes our variable and the theta part becomes our y-axis variable. If this is 90 degree, you should have a graph like this. So the reason I'm trying to show you this is that the sin theta value, I mean, you can see over here that at the increase of the sin theta with the increase of theta is non-uniform. It is slowly becoming less. So আচ্ছা, এখানে আমি sin theta না লিখে রাদার মনে করো এখানে আমি n lambda by d লিখি, তাহলে তোমাদের বুঝতে একটু ইজিয়ার হতে পারে। মনে করো আমি এখানে n lambda by d লিখলাম। এখন মনে করো একটা সার্টেন ভ্যালুর জন্য এই n lambda by d এর ভ্যালু হচ্ছে লেটস সে আমরা এখানে এই এক্সিসে বসাইলাম এবং থিটা ভ্যালু আসলে হচ্ছে মনে করো 10 ডিগ্রি। আচ্ছা, থিটা ভ্যালু 10 ডিগ্রি হইলে এই sin 10 ডিগ্রির ভ্যালু কত দেখো তো? আচ্ছা, এইটা ইকুয়াল টু যে sin থিটা, এটা কি বুঝতেছো সবাই? দেখো তো।
জি স্যার।
শুধু শুধু এটা মুছলাম কারণ এটা তো একই জিনিস, ঠিক আছে? So what I want you to understand that when the value of sin theta is something and you have a corresponding theta angle for the lower value, when the value get increased by the same amount, your change of angle is even bigger. মানে হচ্ছে তোমার 0 ডিগ্রি থেকে 30 ডিগ্রি এবং এখানে মনে করছে 60 ডিগ্রি। If you have a look at this value, sin 0 ভ্যালু হচ্ছে 0, sin 30 ভ্যালু হচ্ছে কত? হাফ, sin 60 ভ্যালু হচ্ছে √3/2, √3/2 ভ্যালু কত? 0.866 না?
দেখে বলি।
হ্যাঁ, 0.866. So this is half. Might as well write it as 0.5, and this one is √3/2, which is 0.866. Now, why am I showing you this? I want you to convince of the fact that equal amount of increase of angle does not give you equal amount of increase over here. But so which means that whenever you will be doubling this thing, your angle is gonna get even bigger. For example, if I want to go from 0 to half to 1, my relevant angle values is gonna be what? 0 degree, 30 degree, and 90 degree. Do you see this pattern? This is how the sin ratio behaves. As you increase the value of theta, for equal change of theta, you have reduced change of sin theta, or vice versa. For equal change of sin theta, you have increased change of theta. If I say the information the other way around, If the value of sin theta has to increase uniformly, the value of theta has to increase in an increasing pattern because the graph is slowly gaining gradient. এই ইনফরমেশনটা কি বোঝা যাচ্ছে?
Yes, sir.
Yes, sir.
So theta value বাড়লে sin theta value বাড়ে but decreasing order এ. So sin theta value বাড়লে theta value বাড়বে but increasing order এ. This is why whenever the ratio of n theta, we have to understand that n lambda by d, এখানে আমাদের lambda একটা constant, d একটা experimental constant, the only thing that actually goes up is n. So n equals to 1 এর জন্য এটার একটা ভ্যালু হয়, n equals to double এর জন্য ডাবল হয়, n equals to 3 এর জন্য ট্রিপল হয়. So for all of those fraction values, you are having an uniform multiple increase of the sin theta value, but that would result in an increasing increase of the theta value. This is exactly why these angles are not equal. They are increasing. So you might as well have this as 10 degree, then this gap will be definitely bigger than 10 degree. If this gap is 12 degree, then this gap will be definitely bigger than 12 degree. This will always come in an increasing order. So as you get further onto the bigger number of n, your spreading compared to the earlier order would be more. So that's another information. This this discussion is actually not unique for a lot of questions, but there is one MCQ which is really important for you to understand this thing. I might as well have skipped this discussion and just to ask you to take my word for acceptance. But this is that MCQ that I'm talking about. Have a look at question number 18. Have a look at question number 18. Which one do you think is the correct response? Looks like a simple question, but it's easy to get confused with this one. That's why I'm showing you this. Which one do you think is the correct response? You can be mistaken. You are allowed to be mistaken. That's what classes are about. Don't be afraid. But do express yourself.
Sir, D হবে.
আচ্ছা,
স্যার সি হবে কি?
Sir, D হবে.
আচ্ছা, আমি একটা একটা করে বলি. Go ahead and discuss the tell you the exact correct answer. Let me give you this thing. A যে হবে না এটা তো সবাই বুঝতেছো because it is impossible not to have a central maxima, right?
Yes, sir.
So A is out of the question. Now between B, C and D we have to pick up the correct response. Now it's a bit difficult to see what is the angle variation over here, but if I just try to convince you that if you look at B and C, do you see that for B the angles are decreasing and for C the angles are increasing? Can you at least see that? It might be a bit difficult for you to see that, but if I zoom on a little bit, maybe it will be easier for you to see that. Can you see it now?
Yes, sir. তাহলে answer C হবে.
আচ্ছা, এখন এই দুইটার মধ্যে obviously C better acceptable because of this angle property. Now D, তাহলে C আর D এর মধ্যে কোনটা হবে না? Here's the deal. What I need you to understand, if you have your first maxima produced at such a small angle, it is not logical that you're not going to have second or third. Have a look. এইটুকু যদি তোমার theta 1 হয়, logically your theta 2 should be somewhere over here. I mean, theta 2 is not available at all, is not supposed to happen for a such small angle of theta 1. Get this point? এখানে খুব অল্প একটা ছোট একটা অ্যাঙ্গেল আমাদের ফার্স্ট অর্ডার ম্যাক্সিমা দেখাচ্ছে না?
Yes, sir.
বাট আমাদের সেকেন্ড থার্ড ফোর্থ এগুলো কিছুই দেখায় নাই, মানে অ্যাপারেন্টলি এগুলো প্রডিউস হয় না, হুইচ মিনস দিস ইজ ডেফিনেটলি নট আ কারেক্ট ফিগার. সো উই আর লেফট উইথ দিস টু. এই দুটার মধ্যে এটা অ্যাকসেপ্টেবল. এখন এটা কেন অ্যাকসেপ্টেবল হবে ওইটার এক্সপ্লেনেশনই একটু আগে তোমাদেরকে ওই সাইন থিটা এবং থিটার গ্রাফটা দিয়ে বুঝাই দিয়েছিলাম যে কেন এটা লজিক্যালি আর ম্যাথমেটিক্যালি এটা কারেক্ট.
বিটা আবার বলবেন ডি হবে না কেন?
আচ্ছা, বিতে দেখাচ্ছে যে আমাদের ইন বিটুইন অ্যাঙ্গেলটা আস্তে আস্তে কমে যাচ্ছে. ইউ ক্যান সি দ্যাট ফ্রম এনি
না স্যার ডি.
Oh, deta na howar, the reason the D is not acceptable because it is showing that the first order maxima n equals to 1, which is this or this, is produced at a pretty small angle, which makes it obvious that the second, at least the second order maxima should be there. Because there is a huge amount of space left. It is proposing that we are only seeing the n equals to 0 obviously, and n equals to 1, but we are not seeing n equals to 2, 3, 4, anything else we are not seeing. But that is not supposed to happen for such a small angle for theta 1. At least theta 2 should be there, which is not present.
স্যার এরকম কি হতে পারে না যে ওরা দেখায় নাই, মানে ওরা দেখায় নাই মানে কি যে এটা প্রোডিউসই হয় নাই, নাকি জাস্ট ওরা এমনি দেখায় নাই, আরো হইতে পারতো?
Have a look, read the question.
যদি ডিতে আরো দেওয়া থাকতো সেকেন্ড ম্যাক্সিমা, তাহলে কোনটা কারেক্ট অ্যান্সার হতো?
Well, if they had given us D with a proper pattern like this, that is increasing gradient, increasing gap size, then we'd be in a real big trouble to choose between C and D. But they wouldn't be usually doing this. This is an obvious wrong answer because the further points are not given. The question says that which diagram shows all possible directions of the light. This says all possible directions. So it's not about whether they drew or not. It's just about the correctness of the figure.
কোয়েশ্চেন ঠিক করে পড়িনি স্যার।
It's all right, no problem. That's why I zoomed out. ঠিক আছে, বুঝে গেছে কি এটা সবার? পোলাবান?
জি স্যার।
আচ্ছা, এই ম্যাথটা একটু সবাই ট্রাই করো। I want all of you to try this thing and see if you can come up with an answer. Number 19. Give it a try. n এর ভ্যালু কত আসে?
4,
সো আনসার কত হবে?
9,
n এর ভ্যালু কি সবার 4 আসছে? আস্তে আস্তে করো। এই ন্যানোমিটারের পাওয়ার, এই 300 লাইন্স পার মিলিমিটার, মিলিমিটার 10 টু দি পাওয়ার -3, এগুলো ঠিক মতন বসাও। বসালে দেখো n এর ভ্যালু 4 আসে কিনা। n এর ভ্যালু 4 আসার কথা। কারণ না মিললে বলো, আমি করে দিব, বাট you should be able to do this, but if you can't, I'll do it for you, no big deal. n এর ভ্যালু সবার 4 আসছে কিনা দেখো। Respond.
Yes, sir.
Either say
Yes,
yes
sir.
or write yes or do something.
স্যার এসেছে।
Okay. Some people are not responding. Should I assume that they couldn't do this, or they are just too lazy to respond? আচ্ছা, সো
স্যার এসেছে।
যদি এর ভ্যালু, যদি n ভ্যালু যদি 4 হয়, তাহলে এখানে কারেক্ট আনসার কিন্তু 4 হবে না। কারেক্ট আনসার হবে হচ্ছে 9, because they are asking what is the maximum number of what is the greatest number of maxima that can be observed. That should be 9, including the central maxima. That should be 9. Beautiful. How about we try number 14 a little bit? This is important, very important for you to observe the figure. The angle that the question gives is not exactly what you should directly place in your equation. Take a good look at the angle.
আনসার সি হবে।
আমার তো আনসার মুখস্থ নাই। থিটা ভ্যালু কত বসাইছো?
30।
30 বসাইতে হবে, ঠিক আছে। দেখো সবার কি সি আসছে?
এখনো করছি,
হ্যাঁ
এখনো অ্যাটেম্প্ট করা শেষ হয় নাই।
আচ্ছা, করে নাও, দেখো কনফার্ম।
আমার সি এসেছে।
আচ্ছা, বিউটিফুল।
জি স্যার, সি আসে।
বিউটিফুল। আর কি কি এখান থেকে দেখানো যায়? এই যে নাম্বার 16টা দেখো। নাম্বার 16 করা লাগবে না, আমি জাস্ট কোশ্চেনটা একটু পড়তে বলতেছি। A narrow beam of monochromatic light is incident normally on diffusion getting. Third order diffraction beams are formed at angles of 45 degrees to the original direction. So what is the highest order of diffraction beam produced by this getting? আচ্ছা, এটা একটু করা লাগবে না, করো এটা। এখানে একটা জিনিস দেখো, ওরা বলে দিচ্ছে যে থার্ড অর্ডার ইজ অ্যাভেলেবল এট 45, সো এন এর ম্যাক্সিমাম ভ্যালু কত হবে? সেইটা আমি একটু করে দেখাই। এটা করার সিম্পল একটা উপায় আছে, তোমরা অনেকভাবে করা যায়, ইটস এ সিম্পল কোশ্চেন। সো the idea is they haven't give us d, they haven't give us lambda, those things are unknown for this question. So if I write this equation for the first information, I can write that d sine 45 equals to, for a degree, equals to 3 lambda. I can write this, right? I want to find out what is the maximum value of n, and maximum value of n এর জন্য আমার লিখতে হবে d sine 90, d sine 90 equals to n lambda. I want to find out this value. Simple, তুমি দুইটা ইকুয়েশনকে ডিভাইড করে দাও, dd বাদ lambda lambda বাদ, so ultimately you will be left with sine 45, which is root 2 divided 1 by root 2 divided by 1 equals to 3 by n. এখান থেকে এখন n এর ভ্যালুটা ক্যালকুলেট করে দেখো কত আসছে।
ফোর
4 আসে, মানে অ্যাকচুয়ালি কত আসছে? 4 পয়েন্ট কত আসছে?
4.24।
আচ্ছা, 4.24 আসলে 2 আসলে 4 হইতো, এটা 0.5 এর বেশি হইলো 4 ই লিখতে হইতো, ঠিক আছে। সো অনেক
জি
সময়
স্যার।
হতে পারে যে আমাদের ডি বা ল্যামডা গুলো থাকবে না, সেক্ষেত্রে আমাদের বুঝতে হবে যে সাইমালটেনিয়াসলি আমরা যদি দুটো ইকুয়েশন লিখি, ওই ভ্যারিয়েবল গুলো আলটিমেটলি আমাদের ইকুয়েশন থেকে ক্যান্সেল আউট হয়ে যাবে। সো ইউ হ্যাভ ডোন্ট লুজ ইওর কাম, জাস্ট রাইট আপ দ্য ইকুয়েশনস এন্ড দেন দ্য ম্যাথ ইটসেলফ will show it to you, so you don't have to bother about that. And then if there are more questions, if there are any difficult questions, আচ্ছা আরেকটা অ্যাডিশনাল জিনিস আলাপ করে নিই, সেটা হচ্ছে we're gonna get a bright and dark sort of pattern using a diffraction grating only when we send a monochromatic light through the diffraction grating. Oh, it's important that this incident wave should come at perfectly vertically onto the diffraction grating. Only then can we use this formula. If this incident light is somewhat at angle or not vertically incident onto this thing, then we cannot apply this formula. For your syllabus, what formula should we apply at that situation is not included. You just have to know that for this formula, d sin theta equals to n lambda to be applicable, the incident ray must fall onto the diffraction grating perpendicularly. That's all you have to say. There is a certain question where it was not perpendicular, so you just have to say because that the incident ray is not falling perpendicular onto the diffraction grating, this formula is not going to be applicable. এটুকু তোমাদের জানা থাকতে হবে। আরেকটা জিনিস যেটা সেটা হচ্ছে, what if other than sending a monochromatic light, if we send a white light onto this slit diffusion getting, সেক্ষেত্রে আমরা কি ধরনের প্যাটার্ন পাবো সেটার একটা ফিগার তোমাদেরকে দেখাই। এখানে আছে এই যে এই ফিগারটা দেখো, এই ফিগারটা, দিস ইজ এ ভেরি ইনফরমেটিভ ফিগার, সো ইটস এ গুড ওয়ান। একটু বড় করি, take a good look at what is happening. If you send white light through a prism, we usually get this. এটা তোমরা অলরেডি ও লেভেলসে শিখছো, the higher মানে red light bends less and the blue light or violet color those bends more. That's for the prism. This is because of refraction. But diffraction হচ্ছে ঠিক উল্টা। diffraction এ যার ওয়েভলেন্থ যত বেশি হবে তার স্পেসিং আউটও তত বেশি হবে. If you wonder why, if I write up the equation, have a look, you should be able to see that d sin theta equals to n lambda. তো এখানে obviously sin theta আর lambda এই দুটোকে যদি আমি individually consider করি, considering the other variables constant, so I can write that these two things are directly proportional, which means the one that has a bigger lambda will essentially give us the same n at bigger angle. So what this figure is going on to show you that if we send white light through a diffraction grating, blue lights would be produced closer and red lights will be produced farther, which means you're gonna get a rainbow pattern over here where this is the blue side. So let's say this is n equals to 1 for blue light, this is n equals to 1 for green light, this is n equals to 1 for red light. এরপরে আমাদের আবার এই বিজিআর প্রডিউস হতে পারে, কিছু কিছু ক্ষেত্রে সেটা ওভারল্যাপও করতে পারে, যেমন এখানে আরেকটা ভালো ফিগার আছে, এটাকে দেখছিলাম, আই এম নট শিওর ইফ আই পুল দিস আপ, এই যে এখানে
তাহলে মাঝখানে কি হচ্ছে, লাইক সেন্ট্রাল ম্যাক্সিমা?
Oh, the central maxima, only the central maxima of this whole fringe pattern would be perfectly white. The central maxima would be observed to be only white spot on the screen. Every other location would have some color. So you can see that violet is produced first, blue, then the entire Vibgyor sequence is presenting itself. এটা একটা realistic figure ছিল এখানে কথা জানেন, এই যে realistic figure টা হচ্ছে এই জায়গাতে. We are sending white light through a diffusion getting slide. This is the diffusion getting. You can see exactly at the center you're getting the bright light. This is the location for the first order maximum for blue, then green, and you can see the whole pattern. This is the red, and here comes the second order for both of them. Do you understand my point? যার ওয়েভলেন্থ যত বেশি হবে তার অ্যাঙ্গেলও তত কি হবে, বেশি হবে. Does it make sense, Polapan?
Yes, sir.
Yes, sir.
এটার উপর বেস করে আমাদের কিছু কোশ্চেন হয়, থিওরিটিক্যাল কোশ্চেন হয়, সো ওগুলো আমরা ওয়ার্কশিট করার সময় ইনশাআল্লাহ দেখব. আজকে ক্লাস আমাদের টাইম শেষ. আমি তোমাদেরকে একটু পরে এমসিকিউ পেপারগুলো আপ করে দিচ্ছি, এমসিকিউ গুলো তোমরা ট্রাই করবা, আর পেপার টুগুলো ইনশাআল্লাহ তোমাদের প্রিন্টেড ফরম্যাটে অল্প সময়ের মধ্যে পৌঁছে যাবে. তোমাদের পেপার টু প্রিন্ট করা আমি শুরু করছি, সো ইউ উইল হ্যাভ ইট উইদিন আ শর্ট পিরিয়ড অফ টাইম. থ্যাংক ইউ ভেরি মাচ. আজকের ক্লাস এখানে শেষ. নেক্সট ক্লাসে মানে কালকে আমরা এই পেপারের কিছু পেপার টু কিছু কোশ্চেন সলভ করব. আই উইল শেয়ার উইথ দ্য পেপার টু কোশ্চেন নেক্সট ক্লাস and we'll go forward. We'll see some problem solving. Thank you. হ্যাঁ বলো.
আমার একটা প্রবলেম ছিল কাইনেমেটিক্সে, আপনি কি একটু দেখতে পারবেন?
কিসে, কোন চ্যাপ্টারে?
স্যার কাইনেমেটিক্স স্যার।
তুমি আমাকে মেসেঞ্জারে আমাকে পার্সোনাল মেসেজ করো অথবা গ্রুপে পাঠাতে পারো. I can discuss with everyone.
আমি গ্রুপে পাঠিয়েছি।
আচ্ছা ঠিক আছে,
আজকে পাঠিয়েছি।
ঠিক আছে, আমি রাতে দেখব, দেখে রেসপন্ড করব. Don't worry about that.
আচ্ছা স্যার, থ্যাংক ইউ স্যার।
Sure. আল্লাহ হাফেজ.
আসসালামু আলাইকুম স্যার।
ওয়ালাইকুম আসসালাম.